Hello, my name's Zach Peterson,
And my name is Aditya Swaranka.
and this is our Project 2, designing a shell tube heat exchanger. Introduction. The purpose of this project is to design a shell tube heat exchanger that will assist in the cooling of the computers of the High Performance Computer Center of MSU. In doing so, we are to design a flow loop, size of the pump, and provide two preliminary design specifications. The design will make use of a water reservoir as the cool side liquid and propylene glycol as the hot side liquid. Some of the design parameters that we were given 10 to the 6 gallons per day of water flow from the reservoir at a uniform rate, a temperature of 56 degrees Fahrenheit, starting temperature of the water, no more than a 3-degree increase in that water, a maximum 120-degree Fahrenheit temperature of the hot side liquid, and heat exchanger maximum length of 25 feet and 12-inch inner diameter of the piping. This is the design that we came up for our closed loop path. It includes 8 90-degree elbows, 2 globe valves, a pump, and the heat exchanger. This path includes going to the reservoir, back to the engineering building on the 3rd floor, and the total length of our pipe is 1,271 feet.
The results that were obtained after running the software, after inputting some values, were as follows. So for the mass flow rate, first of all, we inputted a value of about 5,200, 500,000, sorry, pounds per hour. And for the cold side was about 300,000 pounds per hour. The pressure drops were assigned based on the values we were given through the problem, and same for the temperature differences as well. Um, After inputting these values, especially after inputting the constraint of the pressure difference across the cold side as 3 psi, the pressure drop across the hot side was obtained as 1.6 psi. This 3 psi constraint is also used in the next slide for the calculation of the head loss of, sorry, not the head loss, but the head of the pump. Here, as you see, we have the calculations for the head of the pump. Uh, so the calculated head of the pump was found as 0.324 feet. And to run these calculations, 3 assumptions were made. The first assumption being that the pressure difference across the system, the whole pipeline, is the same as the pressure difference across the heat exchanger. The second assumption was that the starting and ending points are at the same height, since this whole pipeline is a closed loop. Uniform velocity throughout the pipeline, which basically gets rid of the velocity factors in the Bernoulli's equation. After simplifying that Bernoulli's equation, we get this equation right here, where the head of the pump is equal to the total head of the head loss of the pipeline, which is including the minor and the major head losses, and also delta P over rho G across the water for the heat exchanger. This site right here down below, plumbingsupply.com, was used to find the friction losses, constants, and coefficients.
And then total cost. We got this from the Aspen One software. Our total cost comes to 1,200,500. Sorry, $1,257,720. And when divided by our power output comes to $3.81 per watt. As you can see from the table, most of the cost comes from labor, which hopefully during the duration of its life will cost less. Most of the costs will be at the beginning of the project. And yeah. And then here are a couple sites for sourcing our heat exchanger and pump. This is Kerr Pump and Supply. It supplies all types of pumps. We would be looking at a centrifugal pump or something similar. And then if we go over to the heat exchanger website, we were looking at these heat exchangers. They are well within the length requirement. and would run nicely.
So at the end of all these calculations and the results provided by the software, we came to a few conclusions. The first thing that we observed was that the software spits out a value of about 0.33 megawatts as the amount of heat exchanged across the heat exchanger. This clearly does not meet the requirement that's specified in the project document, which is, I think, about 0.6 megawatts. So to tackle this situation, we raised two solutions. The first solution being we can increase the mass flow rate across the heat exchanger. This can be done by adding a stronger pump to drive the PEG or using an even stronger pump across the water pipeline from the reservoir. The second solution is adding an external cooling system that extracts the remaining heat, which is, I think, about 0.27 megawatts. And this can be done by adding an additional refrigeration system across the heat exchanger.
That's our
Thank you.
presentation. Thank you.